resistors in AC and DC circuits. In a circuit, you can either have a direct current source, also known as DC source, or an alternating current source. Okay, so you can have a direct current source, direct current, all right, direct current, beg your pardon, direct current or alternating current, alternating current, alternating current. Now, a direct current is constant in magnitude. It doesn't change, all right? So for a direct current, if it is um 2 amperes, it stays at 2 amperes all through, it doesn't change. But alternating current changes, it changes value. Okay, so in a circuit, you can have resistors through which direct current flows or alternating current flows. Just like a situation where you can have your source to be a DC source or an AC source. As a quick refresher, a direct current is a consequence of a direct voltage, a DC source, like a battery, right? What we'll be dealing with so far in our circuits are DC sources. These symbols that you see here is a DC source, right? A DC source. That means the value of the electrical quantity there is constant, all right? The current or the voltage. So graphically, if we want to represent a direct current, we can have it in this manner. Let's assume this is the vertical axis, and then this is the, so this is current or voltage, current or voltage, all right? The value stays, if it is I or V, whatever you are measuring, the value stays constant for the period of time that it is considered, all right? It doesn't change. That's why it's called a DC. So this is what you have. The value does not change, it stays constant over time. If it is 12 volts, 12 amperes, it stays at that value all through. But alternating current is a current that changes direction periodically, all right? And if it's an alternating current that we are dealing with, what you are going to have is something of this nature. If this is the vertical axis, for example, and then you have the horizontal axis, then you have your current or voltage, you have current or voltage. All these are, what I'm saying at this point is just like a refresher. If you're familiar with your basic physics, you would have done AC circuit. So all these things are explained there. So T. So an alternating current or voltage changes with time. All right. It goes to a maximum value, comes back and like that, goes to a maximum value, comes back and like that. So this is an alternating current. And mathematically, an alternating current or voltage can be represented with the equation V of t, the instantaneous value, is equal to V naught sine omega t, sine omega t. Okay, or we can say I of t, if it's for current, is equal to I naught or Im sine omega t. Okay, so here V of t is the instantaneous value. I of t is also the instantaneous value. V naught is the maximum value, which is the amplitude. I naught is also the maximum value of the current, which is the amplitude. Omega is the angular velocity, and then you have time. Okay, so this is a sinusoidal quantity. So an alternating current can go through a resistor. A direct current can also go through a resistor. What we want to see in this short discourse is how does a resistor respond to in an AC circuit or in a DC circuit? How is power dissipated? All right. So now the simplest circuit element behaves under in different ways under steady or alternating excitation. That's why it matters, all right, a lot to consider this because in medical instrumentation, your DC signals, your AC signals have a lot of role to play in how those equipments function. Okay, a quick refresher. A resistor is a passive element that opposes flow of current, converting electrical energy into heat. We have seen that already. It is called governed by Ohm's law, V is equal to IR. Okay, and then the SI unit of resistance is ohms. Now, R depends on the length, cross-sectional area, not on whether the source is steady or alternating. This is a very important point that we need to pause to consider. So the resistance of a resistor depends on the nature of the material that is used, the length of the material, and the cross-section of the material. It does not depend on whether it is a DC that is flowing through it or an alternating current. Remember that from your basic physics, we have it that resistance, all right, of a resistor, R, is equal to rho multiplied by L over A over A. This is the resistivity. This is resistivity. This is the length. This is the cross-sectional area. This resistivity has to do with the nature of the material, and it is often taken as a constant under a particular range of temperatures. So here, the resistance of a resistor depends on the length, the area, and the cross-section of the resistor. It does not depend on the nature of current or voltage that is passing through it. What we are saying now is that if it is a DC that is passing through the resistor, that does not affect the resistance value. If it is an AC, it does not affect the resistance value. What affects your resistance value is the length and the cross-sectional area. So the key idea here is that a resistor obeys Ohm's law at every instant in time. So the same law describes it for both AC and DC. Okay, that's a very important point. Resistor generally functions based on Ohm's law, which is V is equal to IR. So whether it is an AC that is passing through the resistor or a DC, whether it is a direct current or an alternating current, Ohm's law still holds for your resistor under any condition. All right, whether it's a condition of direct current or alternating current. This is a very important thing to note here. Okay, so Ohm's law states that the current flowing through a conductor, here your resistor is a conductor basically, all right? So we can say the current flowing through a resistor is proportional to the potential difference across its ends, all right? Provided that the necessary physical conditions are kept constant. Okay, so it's a linear relationship. So if you plot your voltage against current, you're going to have this graph. It's a linear relationship, right? You have this graph. So this is the graph that describes the Ohm's law relationship, all right, for resistors. So if a DC is passing through a resistor, it will still obey Ohm's law. If an AC is passing through a resistor, it will still obey Ohm's law. That's what we want to see in this short discussion. In DC circuits, voltage and current are constant. All right, the circuit stays steady as I've earlier explained that DC is steady all through. It is governed by, I beg your pardon, the power dissipated is constant. So for DC circuits, and DC circuit basically is what we have seen so far, is by default the illustrations we have used so far in our examples, we are using a DC source, all right? This symbol stands for a DC source. When you see a symbol like this, right, that's a DC source, all right? DC. So for a direct current circuit, All right. Since the current and voltage remain constant, the power dissipated remains constant. All right. That's the principle here. So for DC circuit, like we have seen, power P is equal to I squared R, or P is equal to V squared over R, V squared over R, or P is equal to IV. So this power remains constant. Why? Because the current and the voltage remain constant. Okay, the series combination is also given by a summation of all the resistance values. While the parallel combination is given by, a summation of all the reciprocals of the resistant values. So the way you sum your total resistance, you get a total resistance for series and parallel combination is as we have seen so far. But when we now come to AC circuits, the same principle applies, but with some level of modification. You know, in a DC circuit, current and voltage, all right, they remain constant. Okay, so in a DC circuit, both current and voltage remain constant. All right, that means it's continuous. From this graph, you can see that the value stays like that. So continuous heat is dissipated. So in a direct current circuit, in a DC circuit, there's nothing like phase. There's no phase relationship because the quantities are not changing value periodically in a sinusoidal manner. We only say that the current and voltage remain, the same. They remain constant. Remain the same doesn't mean they are having the same value, but they just maintain whatever values they are, you know, they are having. Okay, if you have a DC circuit now, maybe this is 10 ohms, and then this is 2 volts, or let's say 5 volts, for example, 5 volts. Okay, applying Ohm's law here, the current flowing in this circuit now, current I, let's use capital letter I in this circuit, I is going to be equal to V over R, right? Which is going to be equal to 5 over 10. So I is equal to 0.5 amperes, right? So when we say that the current and the voltage stays the same, stays constant, it means that this 0.5 amperes, right, will remain 0.5 amperes all through. This voltage, 5 volts, will remain 5 volts all through. So the same here is not meaning that they are having the same values. It means they are maintaining whatsoever value they are having all through the time that the circuit is running. But when you come to um, an AC circuit, there's a slight difference because in an AC circuit, voltage is alternating, and because of that, current is also alternating. So that now brings in what we call a phase relationship. You can now begin to talk about phase when you're dealing with AC circuits, all right? Because the alternating voltage is bringing about an alternating current. But the principle still stands that whether it is in AC circuit or in DC circuit, the response of resistors is based on Ohm's law. V is equal to IR. In resistors, since the voltage is alternating, given by the equation V is equal to Vm, we can say Vm, V maximum. In the previous slide, I used V naught to represent maximum value, all right? You can also say Vm, but whichever symbol you're using, just stay consistent. You can come across maximum value stated as V naught, I naught, or Vm, Im. So the voltage, all right, a in a DC circuit is given by Vm, V of t, I beg your pardon. Let's be more precise with our notations. The instantaneous value V of t is equal to the maximum value Vm sine omega t. So since the voltage is behaving like this, current is a consequence of potential difference or voltage. So the current is also going to be behaving like that. we can say I of t, the instantaneous value of the current, is equal to the maximum value of the current sine omega t, sine omega t. So an alternating voltage is going to produce an alternating current. Okay, so what do we mean by this instantaneous value? We're using the word instantaneous because the values are changing with time. So the term instantaneous is coming into play here because the values of these quantities are changing with time. If you look at this graph now, the illustration I made at the beginning, you can see this graph. The value changes, to a maximum value, comes back, and then it changes like that sinusoidally. So because of this, we can begin to talk about instantaneous values. In DC circuits, we don't talk about instantaneous values because the values remain the same all through. At any instant, the value remains the same. But for AC circuits, the values changes. The values change. So we can begin to talk about instantaneous value, which is the value at a particular time, all right, at a particular time, t. So it's given by this relationship. So Ohm's law still applies. V is equal to IR. It therefore means that, you know, I can apply Ohm's law, but at the end of the day, the voltage and current I'm dealing with are in this form. Vm sine omega t, Im sine omega t, which we are going to be seeing very shortly. Okay, so source voltage varies sinusoidally, as we have seen. V is equal to Vm sine omega t. A resistor responds instantaneously. Take note of these 2 points. All right. The resistor value does not change, but it is going to be responding to the instantaneous value. All right. It therefore means that if the value of the voltage changes, the power in that resistor is going to change. Now, when we say instantaneous value, take a look at this illustration again. That you have a situation where you have the current, I beg your pardon, and the voltage is varying with time. Okay, we have something like this. Pay a close attention here. This is very foundational to this discussion. So we have current or voltage. Anyone we want to represent is fine, either I or V. I or V. And then we have time. So let's pick I, for example. Let's use the red line to represent current in this manner. Now we are saying that the resistor responds to the instantaneous value. What do we mean by that? This graph is just showing that the current is changing with respect to time. At a particular time, maybe the value is, let's say, 1 ampere. It's just an arbitrary illustration. Let's say 0.5 ampere. Maybe at another time again, the value is now 1 ampere, right? And then it keeps going like that. So this resistor is going to be responding according to the instantaneous value of what is the signal that is coming into it. It means that as at the instant where the current is 0.5 amperes, if we calculate the power at that point, P is equal to I squared R, right? So if this resistance value now is, say, 10 ohms, maybe we are dealing with R as 10 ohms, for example, maybe we are taking 10 ohms. At the instant where the current is 0.5 amperes, the power dissipated at that instant is going to be equal to 0.5 squared multiplied by 10, right? Which is 0.5 times 0.5 times 10, right? So that's like saying we have 0.5 times 0.5. Oh, that'll give us 0.25. Let's confirm the value. Okay, so that is 2.5 watts at the instant that the current is 0.5 amperes. Since this current is changing with time, okay, at another instant, the current will now be 1 ampere. Let's say that's the maximum value. Between 0.5 and 1, there are different values too. Maybe 0.6, 0.7, 0.8 until it gets to the maximum value. So at this instant, the power P is going to be equal to I squared, which is 1 squared multiplied by R. R, we said, is 10 ohms. And this is going to give us 10 watts. So you can now see that between this instant and this instant, the power has changed, but the resistance value does not change. That's what we are trying to emphasize here. All right. You know, power dissipated. All right. There's something we mentioned. Okay. R depends only on its own value based on the material and all of that. It does not depend on whether it's alternating or direct. So the resistance value will not change, but because the values of current and voltages are changing instantaneously, the power dissipated is going to be changing instantaneously too. All right, it's going to be changing. If we are using voltage, V squared over R to calculate the power dissipated, voltage is changing, so this value is also going to be changing. That is what we mean by saying that a resistor responds instantaneously. All right, the value does not change all through, but the power dissipated, the energy consumed, the heat is going to be changing as these electrical signals are changing, and it changes very fast. So if we want to apply Ohm's law to a resistor in an AC circuit, we're going to be using the instantaneous value of the current or and the voltage because it responds instantaneously. That's why we are now having this as I of t is equal to V of t over R. Generally, V is equal to IR from Ohm's law. V is equal to IR, right? So the resistor responds instantaneously. And like we said, the word instantaneous is coming into play because the quantities we are dealing with are changing with time. There's an instantaneous value. The next instant, the value changes, and then until it gets to a maximum, comes back to minimum, and then like that and like that. So this Ohm's law still applies, but this Ohm's law now applies to the instantaneous value, which is V of t is equal to I of t multiplied by R. It's still Ohm's law we are dealing with here. All right. This is in an AC circuit. Okay. Now, if we want to make substitutions, it means that your instantaneous value like you are seeing is equal to um, Vm sine omega t for your voltage, maximum value sine omega t, and then Im sine omega t for the current. We can also substitute that into these equations. And then we have it as I of t is equal to V of t over R. All right. Okay. Having said that, we'll proceed to the next key point here. So the next key point we're having is that voltage and current rise, peak, and cross zero together. They are perfectly in phase. There is no phase shift. You see, we said the word phase is coming in here. The word instantaneous is coming in because we're dealing with, periodically varying quantities, right? So the current and the voltage are in phase. That means they are attaining their maximum and minimum values at the same time. By the time we begin to discuss capacitors and inductors, we're going to see there that current and voltage will not be in phase. And when we're dealing with DC circuits, there's nothing like phase, all right? Both current and voltage stay constant. We don't say they are in phase because there's no time varying occurrence with any of the quantities. Okay, so they are in phase means they attain their maximum and minimum values at the same time. Not as if they may be having the same values, but if the maximum value of the current is, say, 3 amperes, and the maximum value of the voltage is, say, 9 volts, what we are now saying is that from between 0 to 9 volts to 0 volts, between 0 to 3 amperes to 0 amperes, it will be happening at the same time for both the current and the voltage in a resistor. All right. Then the next thing is that impedance of an ideal resistor, all right, is equal to the resistance value. There is no reactive component because capacitors and inductors are not present. And then an ideal resistor's value does not change with frequency. So we have said that in an AC circuit, the AC does not change the value of the resistor. It's only the power dissipated, the heat, the energy consumed that changes with time. So frequency, now that we're dealing with, time varying quantities in AC circuits, this component omega is the frequency component. The resistance value does not change with frequency. Okay, so these are some of the key points to note when as we deal with um you know resistors in AC circuits. So let's quickly look at a comparison between DC and AC circuits for resistors. Okay, in a DC circuit, the current and voltage stays steady. We have seen that already, stays steady. But for an AC circuit, the resistor responds to the instantaneous value. In a DC circuit, there's no phase available. There's nothing like phase because the quantities are not time varying. They stay constant. But in an AC circuit, there is a phase relationship. The current and voltage, there's a phase relationship, but they are in phase. All right. The current and voltage are 0 degrees apart. That means they are in phase. They attain their maximum and minimum values at the same time. All right. The impedance is talking about the total opposition to the flow of current in an AC circuit. The impedance, total opposition there is offered by the resistor. All right. And it is real. It has the same magnitude. There's no phase component there. We're going to see all these things when we begin to look at, you know, AC circuits in more details, maybe as we consider resistors and capacitors. Then your resistor is not frequency dependent. It's not, I beg your pardon, there's no frequency in a DC circuit. But in an AC circuit, there is frequency and the resistor does not depend on the frequency like we have seen, right? For a DC circuit, the power remains constant. But for an AC circuit, the power pulsates, it changes with time. Because like we have seen, the instantaneous value of the current is what the resistor is going to respond to at that point to give a particular value of power or energy consumed at that instant.